Hello everybody, welcome to today's video. We'll hop right into it here. Today we're going to be talking about power functions, polynomial functions, and their graphs. So we'll be doing a lot more graphing in the next several videos here. But specifically we'll be recognizing power functions and determining their end behavior, meaning what general direction are these functions headed towards as their inputs either grow to positive infinity or negative infinity. Recognizing polynomial functions, which are very related to power functions. So we will also be looking at their end behavior, but we'll also be looking at determining their degree, their leading coefficient, and then their end behavior to kind of get a general sense of what's happening with these graphs. We'll look at finding the roots, multiplicities, and y-intercept of a polynomial function, and then we'll look at graphing a polynomial function as well. So we will start here with the power functions. So a power function is a function that can be represented in this form here. F of x equals k times some variable x raised to the p power. And both k and p are real numbers. K is what is known as the coefficient, so we'll be using that language from here on out to talk about the coefficients of these power functions, and then an upcoming slide here of the polynomial functions. So I've just written down here a bunch of examples of power functions. Not all of them look like power functions from first inspection, like the one at the very top here. It's the constant function f of x equals 1. So like where's the x? Well, I could write this as maybe 1 times x to the 0. And that would be another way that we could write that. So here we can force it to look like a power function. So yeah, technically a power function here. Next, f of x equals x. So you can always imagine that there's a 1 in front of all of these here. For our coefficient, they can certainly be more interesting, but these are just basic examples. X hopefully is self-explanatory as x to the first power, x squared, x cubed, all looking very much like our definition there. The reciprocal function doesn't quite look like our definition, but I can just use my exponent rules here and write that as x to the negative 1, and same thing with the reciprocal squared function here. And then also for square root and cube root functions, I can write the square root of x as x to the 1/2 power, and the cube root of x as x to the 1/3 power. So just different ways that we could write these power functions here. And then off to the side, I have this question: is f of x equals 2 to the x a power function? So it looks like it might fit the same form here, but actually what we see is that the variable is in the exponent here instead of the base, where in a power function, the variable is in the base and then we're being raised to some numerical power. So this is kind of backwards from what we have as our definition here. So no, but this is an exponential function. And we will talk about exponential functions in upcoming videos. All right, so we want to look at the end behavior for these power functions here, which just means, like I said before, in general, which direction is the function headed as the inputs either grow to positive infinity or negative infinity. So taking a look at the kind of top left quadrant here, we're in some different scenarios. I should also say before we start here that n is a positive integer. So on that previous slide, we had some where they weren't positive and some where they weren't integers. So for what we need here, we need n to be a positive integer. So we'll just be talking about power functions that have an exponent that is a positive integer. So for the first one here, we'll look at even powers. Meaning that the variable is raised to 2, 4, 6, 8, some sort of even power, and then the coefficient in front is a positive number. So something like 2x squared, something like 1/2 x to the 6th. These would all be power functions that have this general shape, whereas x heads to negative infinity, f of x grows without bound, and as x heads to positive infinity, it also grows without bound. So we just get this kind of general U shape, and I always just think, okay, I know what the graph of x squared looks like, and it looks kind of like this. That's an even power, and that helps me keep things straight in my mind. Below, oh, my n got off here a little bit, I am seeing, so this should say negative coefficient. I'm not sure why that happened, but we might see that again. So if the coefficient is negative, then we'll get that the graph flips upside down, which if we think back to our lecture on how we could transform graphs, this should hopefully resonate as making sense. But here we see that as x heads to negative infinity, f of x goes to negative infinity, and as x goes to positive infinity, f of x also goes to negative infinity. So it's just that same situation flipped upside down. And then we can look over here at the odd-powered exponents. So here we have things like 3x cubed, 2x to the 7th, things of that nature. And they have this kind of, it almost kind of looks like the even power, but with the left-hand side just flipped over the axis there. So, I mean, that is actually a lot what is going on. But here we see that as x goes out to negative infinity, the function also goes to negative infinity, and as x goes to positive infinity, the function also goes to positive infinity. So this looks a lot like the graph of x cubed to me, so that is how I remember the general shape here, the end behavior, because since x cubed is odd, I know that this will follow for any odd power. And then again, if we flip that upside down by making the leading coefficient negative, we get the similar thing, but flipped over the x-axis, where now as we head out to negative infinity, the function is growing towards positive infinity, and as the function heads to positive infinity, as the inputs head to positive infinity, the function heads to negative infinity. So this would look like something like negative x cubed. I forgot to do one over here, but something like negative x squared would work for that. So just in general, we're thinking about what's happening at the end behavior. Sometimes it's called the long run behavior. There's some different language that's used for it. So if you see different language in your homework, that all means the same thing: end behavior, long run behavior. All right, so we will look at polynomial functions now. We're going to come back and talk about this end behavior more, since polynomial functions, you can see, have a very similar feel to the power functions we just talked about. So here we will let n be a non-negative integer. So we're even being more specific than we were with the power functions, where we could have some other negative or non-integer numbers. But here we specifically want our power to be a non-negative integer. So a polynomial function is a function that can be written in this very mathy looking form. P of x equals, and we'll break this down, but each of these a sub n, so a sub n minus 1, dot, 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 all the way down to a sub 2, a sub 1, a sub 0. These are all the coefficients. So we see here that each a sub I, and I is going from 0 to n. So if we're starting kind of reading this from right to left, there's a sub 0, here's a sub 1, here's a sub 2, and how many do we need? Well, we need n of them, and we'll talk about why we need n of them. Well, because that is the power here. So that if that's going to be the degree of our polynomial, then we're going to need a sub n, or n number of coefficients as well. And we also say that a sub n can't be 0, because if it was, then we would just take that term off, and that wouldn't matter. So each a sub I x to the I is a term of the polynomial function. So let me clear this up a little bit here. I've scribbled quite a bit already. But each one of these is a term of the polynomial. And this dot, dot, dot here in the middle doesn't mean that there's 3 in the middle and I just didn't want to write those specific 3. That means that this pattern continues along these same lines for however many terms that we need here. We often write polynomial functions so the powers are descending. When written in this form, the leading term will tell us the leading coefficient is a sub n. So looking back to the example up here, a sub n is the coefficient attached to the largest power, and that would be the leading coefficient, and then the degree of the polynomial would be n. And we'll see coming up here that if we want to know the end behavior of polynomials, it is very similar to what we saw for the power function. So let's look at some examples here and determine if each function is a polynomial function, and if so, we'll determine its leading coefficient and degree. So f of x here is negative 3x to the 4th plus 1/2 x cubed minus the square root of 2 times x plus pi. So just looking back to our definition here, we need n to be a non-negative integer. So here we have n is equal to 4, a non-negative integer. They seem to be decreasing from there. We've got 3. There's no x squared, but that's okay. We've got an x to the first, and then we've got this constant at the end being pi. And there's nothing wrong with pi being in there. All of these coefficients are just real numbers. They can be anything that they would like. It's the powers on the variables, the exponents, that need to be non-negative integers. So yeah, this appears to be meeting all of my requirements. So yes, this is a polynomial function. What else were we asked here? Give its leading coefficient. The leading coefficient is -3, and that will tell us something once we start looking at the shapes of these graphs. And the degree is 4, because that is the largest power on any of the variables here. So I'll take a look at number 2 here. G of x equals 2x to the 3/2 power plus x to the -2 plus 1. So here we actually are violating the very first part of the definition here in several ways. First, we have the 3/2 power, so that is not an integer. So we can already be sure that this is not a polynomial function. But also we have a -2 here, which is an integer, but it is negative. It is not non-negative. So here we are failing several conditions, or the same condition in several ways, rather. Not a polynomial. All right. So as I have mentioned a few times, we'll look at the polynomial function end behavior. And here I've only indicated what the end behavior is, because unlike in the power functions, there can be all sorts of numbers of ups and downs and squiggles in here. And we'll talk about those turning points a little bit later. But there can all be all sorts of stuff that happens in between. So we're just focusing on the end behavior here. But it matches exactly what we saw before. So if you already understood and have memorized or understand how that works, for the end behavior for the power functions, the same thing happens here. So looking at even degrees with a positive leading coefficient, this still has the same end behavior as something like x squared. Things heading in the positive direction, in the positive function direction. The function values are heading in the positive direction as the inputs go in either direction there. And then for the odd degree, we'll flip down to the, still keep with even degree, but for a negative leading coefficient, then same thing as before, we would just flip that over the x-axis. Hopefully that's not too surprising, and this would look something like negative x squared, where we're just going to, again, flip that over the x-axis. So then looking at the odd degrees here, we'll just flip colors for fun. Looking at the odd degree, this very much looks like the graph of x cubed. But depending on what we actually get, there might be several, again, bumps and turns in here. So we're just giving the end behavior. And then below it here, if the leading coefficient is negative, then we get something that would look like negative x cubed, where the function is going to positive infinity as the inputs go to negative infinity, and vice versa on this side. So we will need to know this function end behavior as we go forward in trying to look at graphs and understand them and recognize what's going on, or just to be able to graph one of these ourselves. So we'll look at the characteristics of a polynomial function's graph. So the first thing we'll talk about here is the turning point of a graph. It is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. So we'll take a look here. We've got a turning point listed right here because the function is increasing until it hits that point, and then it turns around and starts decreasing, which means right there where it turns around is the turning point. We can see there's another one down here very close to the y-intercept. I wish that those were a little further apart, but that's okay. And then what is important to recognize here is that a polynomial of degree n will have at most n minus 1 turning points. So this is another thing that we'll be using to try and either find the formula of the function from a graph, or to try and actually graph something ourselves. So here there's one turning point here, there's another turning point down here. So there are 2 turning points, which means that this could be at least something with a 3rd degree. So this could be some sort of x cubed polynomial, because there are 2 turning points here. So next we'll look at the y-intercept. So that is this point here where it is intercepting the y-axis. So it is the point at which the function has an input value of 0. So we'll be using that idea here once we start doing some examples. But we see that at the y-intercept, the input value is always 0. So all polynomial functions will have exactly one y-intercept. You will always be able to find one. So that is helpful to know as well. The x-intercepts are going to be the points at which the output value is 0. So kind of just the reverse of the y-intercept. This is where the output values are 0. And then we would have to figure out where these inputs are usually, the input values are. So we know what the output is. It is always 0. And we're looking for... oh, there's something in here that doesn't need to be here. Maybe I copied and pasted a polynomial. I don't need this in here. I must have copied and pasted from above. But for x-intercepts are the points at which the output value is 0, and a polynomial of degree n will have at most n x-intercepts. So sorry for leaving that other bit of information in there. But this is also important to know that if we have a polynomial of degree n, it will have at most n x-intercepts. Now, it could be less, but we know that there is at most n, and that will be helpful. And then lastly here, or second to last, I guess we'll talk about domain and range, but the graphs of polynomial functions are both continuous, which means there's no breaks, there's no holes, there's no jumps in the graph at all. You can draw the whole function without ever picking up your pencil. And they're also smooth, which means there's no sharp corners. So at all of these turning points here, you can see that those are turning around very smoothly, and it's not coming to a sharp edge or a cusp or something like that. That kind of looks like an absolute value. Absolute value functions are not smooth. It has a sharp corner. So polynomial functions are both continuous, no breaks, and smooth, no sharp corners. The domain for all polynomial functions is all real numbers. Another good reason for why this is continuous, and the range is also all real numbers. So no restrictions here for either the domain and the range, which is kind of nice. All right, let's talk about finding intercepts and then the multiplicities of finding the x-intercepts, which will, again, be helpful once we're talking about the shapes of these graphs. So given some polynomial function p of x, the y-intercept can be found by evaluating p of 0. So as we said on the previous page, the y-intercept happens when the input is 0. So we will just input 0 into our function and see what we get. So let's maybe kind of look at these as we're going here. If I want to find the y-intercept, well, this is going to be at f of 0. So I'll just plug in 0 to my polynomial function, 0 plus 1, 0 minus 2 cubed, 0 plus 5. So this is going to give me 1 times negative 2 cubed times 5. So this is going to give me 1, which is still 1. Negative 2 cubed is negative 8 times 5. So this would be at negative 40. So here I know the y-intercept is the point 0, negative 40. So remember that when we're writing our intercepts, either y-intercepts or x-intercepts, we'll always write them as a point and give them as a point. We are finding one of the values because we already know that the other one is 0. So here we've got the y-intercept at 0, negative 40. Next, we'll find the x-intercepts. So let me clear some space here. And we'll look for the x-intercept. So looking at the definition up here, the x-intercepts can be found by solving p of x equals 0. These are also called the roots or the zeros of the polynomial, and those terms just get thrown around so interchangeably that you'll probably hear me use all of them at some point. So just be aware of all those different terms. X-intercepts are also called the roots or the zeros. But as we saw on that previous page, here, this is where all of the outputs are 0, and we need to figure out which input gave us that output of 0. So we'll do that by taking our polynomial here and setting it equal to 0. Since this thing is already factored, this is actually really nice because we can solve each piece of this individually here. So this says either x plus 1 equals 0 or x minus 2 cubed equals 0. Or x plus 5 equals 0. And I think we can, oops, this one should have been 0. So x plus 1 equals 0 to start with, not x plus 1 equals 1. X plus 1 equals 0. Subtract 1 from both sides, we get that x is equal to negative 1, or x is equal to 2. We can essentially ignore the cube that is going on up here because it would have to be 2 for all of those different factors. and then here we would get x equal to -5. So we've got 3 different points here. So if I want to make a little bit of space so I can write down what the x-intercepts are. The x-intercepts are at -1, 0. So we found that the x was -1, the output is always 0. That's what it means to be an x-intercept. We've got 2, 0 from here, and we've got -5, 0 from the last one. So there we go. There are our x-intercepts. Actually, before I box that, the last thing we want to talk about here are the multiplicities for each of these roots. So back up to our definition here. The number of times a given root appears in the factored form of the equation of the polynomial is called the multiplicity. So if I want to write down the multiplicities here, the multiplicity for the x-intercept -1, 0, since there is just a 1 on that factored form, then this has a multiplicity of just 1. Since the power on x minus 2 is 3, that means that the multiplicity of 2, 0 is 3. And since the power on x plus 5 is also 1, the multiplicity for the x-intercept -5, 0 is also 1. So there we go. Here are all the x-intercepts and their multiplicities. Well, I guess we did this in backwards order. I was supposed to do the roots first and then find the y-intercepts, but we got them all anyway. I didn't read the example before I started reading the definition. So there we go. We've got the y-intercept, we've got the x-intercepts, and we have all of their multiplicities. All right, so you might be wondering, why the heck do I care about a multiplicity? I mean, I get the root, right? I know it exists. It's right where I thought it was going to be. What's it matter if there's multiple of them? So if a polynomial contains a factor of the form x minus h to the p, like we saw in that previous example, the behavior near the x-intercept h is determined by the power of p. So here we can see a few different examples. And we say that x equals h is a 0 of multiplicity p to finish off that definition. We have a few different cases here. Case 1 and case 3 are somewhat related, but they just act a little bit different. So the graph of a polynomial function will touch and bounce off the x-axis at zeros with even multiplicities. So here in this example, we have p equals 2. So this would be something like, x squared. What happens here is that it comes down and it bounces. So it's still intercepting that x-axis, but it's just touching it and it's bouncing right off. The graph will cross the x-axis at zeros with odd multiplicities. So it's going to cross through. So if it's even, it bounces off. If it's odd, it crosses through. So if it's just a single 0, then it'll just pass straight through. Nothing interesting happens there. If it is an odd multiplicity like 3, 5, 7, etc., then it still passes through, but it has more of this kind of like x cubed shape to it. So here I have p equals 3, and you can see it does have that very x cubed shape to it. So, and here this has a very much just x to the first power shape to it, just like a line. So just remembering those examples helps me remember what the local behavior is at each of these roots. If it's just a single 0, it acts just like a line does. If it's an even power, well, it's going to act like a parabola does. And if it's an odd power, it's going to act something like an x cubed power, or an x cubed function. So here we are asked to do an example. We're going to write an expression in factored form of the polynomial of least possible degree for each of these graphs below here. So I know I'm going to try and write something of the form f of x equals some leading coefficient, and then we'll have things factored out here raised to some different powers here. So that is kind of our goal here. So let's see if we can't start plugging in some pieces by taking a look at this graph here. So first thing I notice is the end behavior as it's heading both directions. We're heading to positive infinity, which tells me that this must be some sort of even degree. Now I could also use the number of turning points here to figure out what the least degree must be here. So since there are 1, 2, 3 turning points, then the least degree is going to be 4. So remember that there's always n-1 turning points, or it'll be at most n-1 turning points for a graph, a function of degree n. So here we have 3 turning points, which means this could be at most, or at least degree 4. Could be more, but we know it's at least degree 4. Okay, so we've got that going for us here. I think if we're going to start trying to build our function here, what we should look at are the zeros. So we've got some different zeros here. If I change colors, let's go to purple. We've got a 0 at -2, we've got a 0 at -1, and we've got a 0 at 3. We can see what is happening at these roots. Either they're passing through, or they're bouncing off and going the other way, and we can use what we know about multiplicities to get that going here. So if I'm going to try and write this function like we were before, f of x equals a. Now I know that since there is a root at -2, I can write x plus 2. That is x minus -2. Whenever we're writing the roots, it's always in x minus whatever the root is. So x minus -2, x minus -2 is x plus 2. So, whoops. So I will just skip straight to that if I could stop erasing stuff. All right, we also have another 0 at -1, so that's going to be x plus 1. And then we've got another root at +3, so this will be x minus 3. Now, we need to look at the power on each one of these factors to make sure that we've got it straight here. So like I actually just said, I guess I could redraw those arrows that I just erased. At -2 and -1, it's just passing through. It's not flattening out at all. So, you know, if it was flattening out, we might say a degree 3 or something like that. But since it's just passing through, we know that it's just powers of 1 on both positive x plus 2 and x plus 1. But at the root 3, it's bouncing, which means that it's got to be even. And now, so, you know, if it's even, it could be 2, 4, 6, 8, but we know that the degree here is, well, I guess it's at least 4, so I guess we could choose, but I guess we're just going to go with a square because that makes things easy for us here. So here we've got most of it figured out. We've got the only thing left to look at is what the leading coefficient might be here. So once we figure out a, we will have it all put together. So to figure out what a is, what we're going to do is look at the y-intercept, which is at 3. So I know that f of 0 is equal to 3. I'm going to leave a bunch of space here because I want to go plug in 0 everywhere, but I know it's going to be equal to 3 when I'm done because that is the function value at 0. So a is still a. This is what I'm hoping to solve for here. And then I'm going to have 0 plus 2, 0 plus 1, 0 minus 3 squared. And now, hopefully, I should be able to solve for a. So this says a times 2 times 1 times -3, whoops, -3 squared, getting ahead of myself there, is equal to 3. So this says a times 2 times 9 equals 3. So what's this? 18a equals 3. A is equal to 1 over 6. So now I know what a is. I can just go fill that in. So in fact, that's literally what I'm going to do. This is the one I want to change. I know that this is 1 over 6. So there we have it. In fact, let me get rid of the little ones there because we don't need them. And there we have it. There is the function written out in factored form for the graph for number 1 there. All right, let's take a look at the next one. So let me make a little space. All right, so looking at just the overall shape here, as we're going out to negative infinity, the outputs are going to positive infinity, and then they're going the opposite way as the inputs grow. So this means that this looks something like the graph of negative x cubed. So that tells me that the leading coefficient must be negative. I didn't write that down before. The leading coefficient's gonna kind of fall out once we solve for it, no matter what. So that's kind of nice. But we know the leading coefficient will be negative, but we know that the degree will be odd. So we've got an odd degree. Let's look at these turning points here to figure out what that degree might be at least. So here we've got 1, 2, 3, 4 turning points, which means that this is going to be at least degree of 5. So this is at least degree 5. So we'll keep that in mind as we're putting things together and looking at our multiplicities and making sure that we're getting what we want here. So again, what we want to do is write this as some function. We'll go with g of x this time is equal to some leading coefficient. And then we can use the x-intercepts to figure out how to write our factored form here. So looking at our x-intercepts, again, we've got one at -2. That is just mostly coincidence. So this is going to be x plus 2. Now there's a bounce there, so we'll have to come back and add some sort of degree here. And then what we've got next is one at -1. So x plus 1. And then we've got another 0 at +1. So that's going to be x minus 1. And there, I might go back and erase that, but there you can see that it's not just passing straight through, but it does have a little bit of a bend to it. So we'll have to think about what that multiplicity might be. All right, well, let's just do that right now. If I'm taking a look here, we've got a bounce, so that means that on x plus 2, or at least got to put a 2 there, and then same thing for x plus 1. And then on the x minus 1, we're getting a little bit of a bend there, so we know that this has to be at least 3. It's passing through, but it's not going straight through like a line. It's doing a little bit of a slowdown. So we know we got at least that there. Okay, so it looks like right now we're at degree 7, which is fine. We knew we were looking at least degree of 5, but degree of 7 is perfectly fine. So now if I want to find what that value of a is, again, we'll use what our y-intercept is, which is up at 4. So I know that g of 0 is going to be equal to a, 0 plus 2 squared, 0 plus 1 squared, 0 minus 1 cubed is equal to 4, since I know g of 0 is 4. So we'll do very much like we did before. Might regret not having enough room here, but let's see how this works out. So a, and then we've got 2 squared, we've got 1 squared, and we've got -1 cubed equals 4. So this is going to give me 2 squared is 4, that's 1, and that's -1. So this says -4a equals 4, which means that a equals -1. So we can just go plug that in where we had our a placeholder, and we will put in just a negative in front of it here. So we can box that there. So here we have gotten our function from the graph, negative as our leading coefficient, -1, x plus 2 squared times x plus 1 quantity squared times x minus 1 quantity cubed. All right, so finally here we are going to sketch a graph so just basically the opposite of what we just did. Before we were given the graph and figured out what the function looked like. Here we're given the function written out, and we are going to try and get the best graph we can here. I'll just maybe point out straight away that we're not going to do the y-intercept because it happens to just be some huge value here. But in order to make this problem somewhat interesting, that kind of needed to happen. So if we're looking at the degree here, this will help tell us kind of the direction of what our end behavior should be. So if I'm looking at degree, I've got a 2 here, a 4 here, so I'm already at degree 6, and then there's a 1 here. So degree 7 is what we're looking at. And maybe let me change to a little bit more of a visible color. So we have got degree 7, and then the leading term here is negative 5.5. So putting those two facts together, I know that I'm going to have kind of things going in opposite directions for the end behavior because of the odd degree. And since the leading term is negative, it's going to be going this way and this way. So it kind of looks like the negative x cubed behavior flipped upside, or yeah, the negative x cubed behavior, not flipped upside down. It had already flipped upside down. Okay, so there we've got that. So, you know, that's just kind of placeholder endpoints. I can change those if I want. So the zeros here are going to be looking at this first one. This means I have a 0 at 1/2. So if you set that equal to 0 and solve for it, you would get 1/2 there. We've got another one. X plus 3 means we have a 0 at negative 3. And then this x minus 4 means we have a 0 at positive 4. And then we'll look at the multiplicities for each one of those. So I didn't write this out in a very nice way, but the multiplicity for 1/2 is 1. The multiplicity for negative 3 is 4. So that means we're going to have a bounce there, and that bounce is going to kind of hang on for a second. It'll be a little bit flatter. And then the multiplicity for 4 is 2. So we're going to have a bounce there as well. All right, let me clean up my function a little bit. So that's still going that way. All right, so let me plot these zeros on here and kind of think about what's going to happen around those spots. So I know that I'm going to have a 0 at negative 3. So 1, 2, there's negative 3. We got a 0. I know it's going to bounce off of that. So if I already know that the end behavior is going to positive infinity, then that means this is going to come down and hit that intercept and bounce. Now, I don't know what's going to happen after that, but I can at least kind of get that sketched in there. So that's at negative 3. We've got another one at 1/2. So let me put 1, 2, 3. I know I'm going to have another one at 4. So just kind of getting some hash marks in here. I'm going to have another one at 1/2 here. Oh, let me label this point since I need to be labeling my points here. This is the point negative 3, 0. And then at this point here, which is 1/2, 0, since the multiplicity for 1/2 is 1, that must mean that it passes through 1/2. So this must come up somewhere and then turn back around, and then it's just going to pass straight through that guy there. And then looking, we have another 0 at 4. So 1, 2, 3, 4. And this has a multiplicity of 2. So we're going to get a bounce off of there. So this must turn around and then bounce off of here and then head out that way. And I missed my initial arrow, but that's okay. We can easily deal with that. So let me just take a look at my number of turning points here. There's 1, 2, 3, 4 turning points. This is degree 7, so that's fine. This is the point 4, 0, just to make sure I have everything labeled properly here. So let me just read the instructions. I don't think I ever went through the entire thing here. Credit for graphing is based on correctness, cleanliness, proper end behavior, which we've gotten here, illustration of proper behavior near the zeros. We've got bounces, we've got pass-throughs, and the labeling of the x-intercepts, which we've done. And the y-intercept does not need to be plotted according to the instructions. But hey, let's go for it anyway. I think that the reason we're not doing it is because it's going to be a very large number, but why not? Let's just do it for completion here, and we can get our y-intercept labeled as well, even if it turns out to be a very large number. So I'm just going to create a little bit of space here, and then at the bottom we will think about the y-intercept. That's going to be at 0, so I'm plugging 0 into the polynomial function here, and I'm going to get negative 5.5 times, so if I plug 0 into here, I'm just going to get negative 1. If I plug 0 into here, I'm going to get 3 to the 4th power. And if I plug 0 into here, I'm going to get negative 4 squared. And this is what we're trying to find, so we're not setting that equal to anything yet, but we're just going to compute this number. So what do we get here? Negative 5.5, negative 1, so that's going to become positive. 3 to the 4th is 81. And negative 4 squared is 16, so I don't know that one any better than anybody else, but I can pull up a calculator quickly. So positive 5.5 times 81 times 16 is 7128. So this point up here is 0, 7128. So I think if we had to graph that, you know, we're not going to put in, obviously, 7100 little hash marks there. So maybe that is the reason that we weren't asked to plot that point, but I'll plot it on there, and now our y-axis is just real squished in its scale, and that's fine. So I think if you went into Desmos and tried to plot this, you would get a shape that didn't quite look like this, but would look like very squished together just because that y-intercept is so crazy. But there we have it. We've got this thing graphed. All right. That brings us to the end of this lecture. So I wish you well, and I will see you in the next one. If you have any questions, please let me know.